Steel, the backbone of our civilization. It's in the bridges we cross, the buildings we live in, the cars we drive, and even the tools we hold in our hands. But how exactly is steel made from simple rocks deep within the earth? It all begins with iron ore, a natural rock that contains compounds of iron and oxygen, mainly hematite and magnetite. To obtain pure iron, this oxygen must be removed. That happens inside one of the most impressive machines ever built, the blast furnace. In a blast furnace, 3 key ingredients are added layer by layer: iron ore, coke, and limestone. Coke, a purified form of coal, burns at extremely high temperatures, generating gases that remove oxygen from the ore dot. This chemical reaction produces molten iron, which collects at the bottom of the furnace. At the same time, limestone combines with unwanted impurities like sulfur and phosphorus, creating slag that floats on the surface and can later be removed. The molten iron that comes out is called pig iron. It contains about 3–4% carbon, along with traces of other elements. Pig iron is very hard but also brittle. It breaks instead of bending. To turn it into steel, we must remove most of that carbon and purify the metal. When the furnace is tapped, 2 layers come out. The lower layer, molten pig iron. The upper layer, slag. At this point, we have iron, not yet steel, but it's the crucial first step toward creating one of humanity's most versatile materials. If you enjoy educational content like this, don't forget to like, subscribe, and share this video with your friends. When molten iron leaves the blast furnace, it looks like a river of fire, glowing orange, dense, and more than 1,500 degrees Celsius hot. But this is still not steel. It's crude iron full of carbon and unwanted impurities such as silicon, phosphorus, manganese, and sulfur. To transform this molten metal into high-quality steel, these impurities must be removed with precision and speed. That's where the oxygen converter, also known as the LD converter, comes into play, a technological breakthrough that revolutionized modern steelmaking. The converter is a massive steel vessel lined with heat-resistant refractory bricks. It can hold hundreds of tons of molten iron at once. When the hot pig iron is poured inside, a water-cooled lance is lowered from above, blowing pure oxygen into the molten metal at supersonic speed. The oxygen reacts instantly with the excess carbon, burning it away and forming carbon monoxide and carbon dioxide gas. The same process also removes other elements, silicon, phosphorus, and manganese, which are oxidized and absorbed into the slag layer floating on top. This reaction is extremely exothermic. It releases enormous amounts of heat. Temperatures can rise above 1,700 degrees Celsius, keeping the steel molten even as impurities are removed. The spectacle is intense. Bright white flames burst from the converter mouth, and sparks fill the air like a glowing storm. Within about 20 to 40 minutes, the entire composition of the metal changes. The carbon content drops from several percent down to less than 0.3%, and what remains is pure, refined steel, strong, flexible, and ductile. It's one of the most dramatic transformations in all of industry, from brittle cast iron to the powerful, versatile steel that shapes our world. At this stage, alloying elements can be added to fine-tune the metal's properties. Chromium makes it corrosion-resistant. Nickel improves toughness. Molybdenum increases strength under high stress. Vanadium and tungsten boost hardness and wear resistance. Each combination creates a new type of steel for a specific purpose, from stainless cutlery to aircraft engines. In modern steel plants, the entire process is controlled by computers and sensors that continuously measure temperature and chemical composition. Every batch of steel is precisely engineered to meet exact specifications. When the oxygen blow ends, the molten steel is transferred into a ladle furnace, where it undergoes secondary refining, removing dissolved gases like hydrogen and nitrogen and making final adjustments to the alloy mix. Only after this stage can we truly call it steel, clean, strong, and ready to be shaped into the foundation of modern life. After the refining process and the oxygen converter, the steel is finally clean, chemically balanced, precisely alloyed, and incredibly hot, still around 1,600 degrees Celsius. But it's not useful yet. To become a beam, a sheet, or a rail, it must be solidified and shaped. This is where one of the most advanced and continuous processes in modern metallurgy begins: continuous casting. In the early days of steelmaking, molten steel was poured into large molds, forming ingots. Once solidified, each ingot had to be removed, reheated, and rolled, a slow and wasteful method. It often produced structural flaws like cracks, gas pockets, and uneven composition. Continuous casting changed everything. In this modern method, molten steel is poured into a copper mold cooled by water, known as a crystallizer. As soon as the liquid metal touches the chilled mold walls, a thin, solid shell forms, just a few millimeters thick, while the inside remains molten. The semi-solid steel strand is continuously pulled downward, supported by rollers and sprayed with cooling water until it hardens completely. The result is a continuous slab of solid steel, several meters long, which can then be cut to size using mechanical shears or torches. Depending on the mold's shape, the product can take one of several forms: slabs, wide and flat, used for sheet and plate production; blooms, thicker and more square, used for structural profiles; billets, smaller and round or square, used for wires, rods, and bars. Continuous casting is fully automated. Sensors monitor temperature, pulling speed and cooling intensity in real time to prevent cracks or defects. It's one of the most efficient processes in heavy industry, reducing waste, saving energy, and producing uniform steel of exceptional quality. Once solidified, the steel moves to the next phase, hot rolling. Here, massive rolling mills with enormous pressure squeeze and elongate the glowing red slabs into their final forms. At these high temperatures, steel behaves like thick dough, malleable and shapeable. It can be rolled into thin sheets for car bodies, thick plates for ship hulls, or long rails for railways. Hot rolling also refines the steel's internal grain structure. Under pressure, the metal's microscopic crystals elongate and align, increasing strength and toughness. As it cools, the surface oxidizes slightly, forming a dark layer called mill scale, which is later removed by water jets or acid cleaning. By the end of this stage, steel has transitioned from a molten material to a solid industrial product, strong, uniform, and ready for its final transformation. But its true character, hardness, flexibility, resistance, still depends on the final thermal and chemical treatments that come next. By now, the steel has been cast, rolled, and shaped, but its journey is far from over. What truly defines steel's character isn't just its chemical composition, but the way it's heat-treated and alloyed. These final steps determine whether the metal becomes as flexible as a spring, as hard as a knife blade, or as resistant as stainless steel used in skyscrapers and satellites. Heat treatment, controlling the inner structure of steel. Heat treatment is a carefully controlled process of heating and cooling steel to alter its internal crystalline structure and mechanical properties. There are three main techniques used across the world: hardening, tempering, and annealing. Hardening involves heating steel to a high temperature and then cooling it rapidly, often in water or oil. This sudden change traps carbon atoms in the crystal lattice, forming a hard phase called martensite. The result? Steel that's extremely hard but also brittle. Tempering comes next. The hardened steel is reheated to a lower temperature and cooled slowly, releasing internal stresses. This process restores toughness and elasticity, creating the perfect balance between strength and flexibility. Annealing is used when ductility and softness are desired. Steel is heated and then cooled very gradually, which allows its crystal structure to realign and relax. This makes the material easier to machine, bend, or weld. Through these processes, metallurgists can program the steel's behavior to match the exact requirements of its future purpose. Alloying designing steel for every purpose. To push steel's capabilities even further, various alloying elements are added to fine-tune its properties. Each element changes how steel behaves. Chromium improves corrosion and oxidation resistance. It's the key ingredient in stainless steel. Nickel adds toughness and strength, especially at low temperatures. Manganese improves hardness and helps remove sulfur impurities. Molybdenum increases resistance to high temperatures and mechanical stress. Vanadium refines grain size, improving both hardness and durability. Tungsten enhances hardness and heat resistance, ideal for cutting tools. By adjusting these proportions, engineers create thousands of steel grades, each suited for a specific task. From the reinforced skeleton of skyscrapers to surgical scalpels, from jet turbines to bicycle frames, every product has its own unique recipe. Types of steel and their applications. Steel is often classified by its carbon content. Low-carbon steel, less than 0.25% carbon, soft, ductile, and easy to shape, used in construction and automotive panels. Medium-carbon steel, 0.25–0.5% carbon, stronger, used for axles, shafts, and machine parts. High-carbon steel, over 0.5% carbon, extremely hard and wear-resistant, perfect for tools, springs, and blades. Beyond these, there are stainless steels, heat-resistant steels, and tool steels, each engineered to thrive in its specific environment. Modern steelmaking and recycling. In today's world, steel production isn't just about strength, it's about sustainability. More than 70% of global steel is now made from recycled scrap using electric arc furnaces. These systems melt old steel using electricity instead of coal, drastically reducing carbon emissions. Steel is infinitely recyclable. It can be melted and remade countless times without losing quality. Every recycled car, ship, or skyscraper can be reborn as a new beam, bridge, or tool, a perfect example of a circular economy in action. The legacy of steel is more than just metal. It's the material that built our cities, powered our machines, and connected our world. Every rail, every beam, every tower is a silent witness to human progress, forged in fire and refined by knowledge. From raw rock to engineered perfection, steel represents our mastery over nature's elements. It's strong yet flexible, ancient yet modern, ordinary yet extraordinary. And as long as humanity continues to build, explore, and create, steel will remain the foundation of civilization itself.